Good evening, children.
Good evening, ma'am.
Good evening. Good evening, children. I've shared my screen. Is it visible?
Yes, ma'am.
Okay. So as I had shared with you earlier, today we are starting this chapter circles. So in today's session, I want to discuss exercise. What is this? (10.1). Okay. Let's see if we can discuss the answers to exercise 10.1 as well as 10.2. Okay, so we'll not be writing anything through the session today. We'll just understand the contents and I'll share the images with you later. Okay. So to start off, we'll need to know two theorems. The first one is the tangent at any point of a circle is perpendicular to the radius through the point of contact. Circle, center, line L touches the circle at P. So L is a tangent to the circle at P. P is called the point of contact. P is the point of contact. The point where the tangent touches the circle is called the point of contact. So P is the point of contact. Now through P, the radius drawn through P, the radius which is drawn through the point of contact, this radius is perpendicular to the tangent. The radius which is drawn through the point of contact, this is the point of contact, the radius drawn through the point of contact. So you'll have to join the point of contact to the center O to get the radius. So this radius drawn through the point of contact is perpendicular to the tangent. So radius tangent 90 degrees at the point of contact. We know a tangent is a line that touches a circle at exactly one point. A secant is a line that intersects a circle at two distinct points. A secant is a line that intersects the circle at two distinct points. A tangent is a line that intersects a circle at exactly one point. Okay, so this is one theorem. We'll not see the proof to the theorem in the session today. This is one. The second one is the lengths of the tangents drawn from an external point to a circle are equal. Now, before we understand this, circle, when you're given a point inside the circle, okay, when you're given a point inside the circle, you cannot draw any tangent to the circle given a point inside the circle. Now, through this point, you cannot draw any tangent to the circle. You can draw lines, but none of those lines will be tangents to the circle. Circle, a point inside the circle. You can draw many lines passing through this point inside the circle. You can draw infinitely many lines, but none of those lines can act as a tangent to the circle. So given a point inside the circle, no tangent can be drawn. No tangent can be drawn passing through a point which lies inside the circle. No tangent can be drawn passing through a point that lies inside the circle. Now, when you're given a point, see, with respect to the circle, there are three different positions. With respect to a circle, there are three different positions. Point inside the circle, point on the circle, point outside the circle. point inside the circle, outside the circle, on the circle. So inside the circle, there is no tangent that can be drawn passing through this point which is inside the circle. On the circle, exactly one tangent can be drawn passing through this point which lies on the circle. Exactly one tangent can be drawn passing through this point which lies on the circle. And from this point which lies outside the circle, two tangents can be drawn. Let me just take the point here so that it's comfortable for me to draw. So two tangents can be drawn. If this is the external point, P, then exactly two tangents can be drawn to the circle from a point given outside the circle. They're lines, so they're lines, so you can just produce them. Circle, point lying outside the circle, exactly two tangents can be drawn through a point lying outside the circle. Okay. Now the statement here is the lengths of a tangents drawn from an external point to the circle are equal. So circle, you can see here, circle with center O, A is the external point, AP and AQ are tangent segments. What is the difference between a tangent and a tangent segment? A tangent is a line. Okay. This is a tangent. A tangent is a line. This tangent touches a circle, say at P. A tangent is a line. What is a tangent segment? Like you say, a line segment is a part of a line. A line segment is a part of a line. In the same way, a tangent segment is a portion or a part of the tangent. Okay. Now, when we take a point outside the circle like this, we know that two tangents can be drawn, right? Excuse me, it's not very neat, my drawing. Okay. So they are lines, so they go on like this. These are the two tangents from this point outside the circle. If I call this A and B, the points of contact is A and B, and P is the external point. Now see here, what is PA? PA is a segment of the tangent L. And what is PB? It's a segment. It's a part of the tangent M. PA is a part of the tangent L. PB is a part of the tangent M. So PA and PB are called the tangent segments. PA and PB are called the tangent segments, which are, like some portions of the tangents. But tangent segment, they are strictly, see, when we say tangent, we are mostly referring to the tangent segment. So it's like actually situational. You need to understand if it is a tangent or a tangent segment based on the situation. In this figure, you can see a circle with center O. A is the external point. AP and AQ are the two tangents from the external point A to the circle. So they are tangents, meaning they are tangent segments. AP is a tangent segment, AQ is another tangent segment. Okay, we need to show that these two tangents are equal. The tangents drawn from the external point to the circle are equal. AP is equal to AQ. So this is a statement which is true. It's a theorem. So for this, you'll have to show that these two triangles are congruent, and CPCT, you get the result AP is equal to AQ. So the tangents from an external point of the circle are equal in length. AP is equal to AQ. You can show that these two triangles are congruent, and CPCT, AP is equal to AQ. Okay. Prove that in two concentric circles that have the same center but different radii are concentric circles. Okay, so prove that in two concentric circles, the chord of the larger circle. So this is the outer circle is the larger circle. Outer circle is the larger circle. The chord of the larger circle. So AB is a chord to the outer circle, which touches the smaller circle. Yes, we see that the chord AB touches the inner circle at P. So AB, is related to the outer circle as well as to the inner circle, but the relationship is different. This line segment AB is related to both the circles, the outer circle and the inner circle. To the outer circle, AB is a chord. To the inner circle, AB is a tangent at P. P is the point of contact. It's a tangent at P. Okay. So prove that in two concentric circles, the chord of the larger circle, which touches the smaller circle, is bisected at the point of contact. So this is the point of contact, is bisected at the point of contact, meaning you'll have to prove that PA is equal to PB. We'll have to prove that PA is equal to PB. The line segment is bisected, meaning cut into two equal pieces. PA is equal to PB. All right. So, this is 90 degrees. The diagram may not be given. You will have to draw the diagram. Okay. You will have to draw the diagram. So, in that case, you should know that this is 90 degrees because this is the point of contact. P is the point of contact of the tangent. And through the point of contact, we have a radius. So this radius will be perpendicular to the tangent. So 90 degrees here. And then join OA and OB. Show that these two triangles are congruent. OPA congruent to OPB. OPA congruent to OPB. So CPCT, you will have the result PA is equal to PB. This is one way of doing. This is one way of doing. CPCT, you will have the result PA is equal to PB. Okay. What did I say? This is 90 degrees by the theorem because radius tangent perpendicular here. That's by the theorem. Then I said join OA and OB. Show that these two triangles are congruent. The rule will be RHS because right angle. Then OA is equal to OB because radius of the outer circle. OA and OB, they are the radii of the outer circle. So RH and OP is the common side. OP is the common side. So by RHS congruence criterion, the two triangles are congruent. So PA is equal to PB, CPCT. If PA is equal to PB, that means the line segment AB is bisected. Okay, at the point of contact. Otherwise, you can use the theorem. Now, this is 90 degrees because radius perpendicular to tangent. And then go down to 9th standard. We have learned that the perpendicular from the center to a chord bisects the chord. The perpendicular from the center to the chord bisects the chord. So AB is a chord to the outer circle. And what is OP? It's a perpendicular from the center to the chord. So it bisects the chord. So PA is equal to PB. That's it. You just have to write two things. AB, I repeat, AB is a tangent to the inner circle. It's a chord to the outer circle. So when it is a tangent to the inner circle, you have this result OP is perpendicular to AB. Okay. Now treat AB as, now this is because AB is a tangent. OP is perpendicular to AB when AB is a tangent. Now treat AB as a chord. Treat AB as a chord. OP is perpendicular to the chord AB. So the perpendicular from the center to the chord bisects the chord, theorem. So PA is equal to PB. Therefore, PA is equal to PB. You can do it in these two ways. Yeah, see, I have both the, see, here I've proved using congruency. You can see here. I'll share the images later, children. Here I've proved using congruency, and here by using the theorems. We know that the perpendicular from the center to a chord bisects the chord. Therefore, chord AB is bisected at P. Okay. This one needs similar triangles. Just give me some time. We'll do this. We need to know similar triangles to understand this. So I'm just leaving this for the time being. Yeah. From a point Q, the length of the tangent to a circle is 24 centimeters. And the distance of Q from the center is 25 centimeters. The radius of the circle is. So this is standard diagram, children. So when you read a question like this, you know, this is the radius, this is the radius, this is the tangent segment, and this is the distance between the center and that external point. I'll just do it again. See here, circle, circle. Okay, I'm not marking the external point because I'm scared if I can connect it. So I'm not marking the external point, but there is an external point. Okay, center of the circle, radius. All right. Now draw the tangent and join the center to that external point. Yeah. So what is this? Center O. From a point Q, the length of the tangent. So this is Q. From a point Q, the length of the tangent. Okay. And the length of the tangent to a circle is 24 centimeters. So let me call this P. This is 24. And the distance of Q from the center. The distance of Q from the center. So this one, OQ, is 25 centimeters. The radius of the circle is. So we know this is 90 degrees because radius and this is the tangent. So at the point of contact, they meet at right angles. So this one is a right triangle. The hypotenuse is 25 centimeters. So we have OP square plus 24 square is equal to 25 square. Q is the external point. OQ is the distance between the center and the external point. OQ is the distance between the center and the external point. PQ is the tangent segment. Which is the length of the tangent here? I told you tangent segment, tangent. So here it's a tangent segment. PQ is a tangent segment. Its length is 24. So you can find the radius using Pythagoras theorem. So here in this figure, TP and TQ, you can see T is the external point. T is the external point. TP and TQ are two tangents to a circle with center O. So that angle POQ is 110 degrees. POQ is 110. Then PTQ PTQ, this one, this angle is equal to PTQ, this angle. So you can find this using the angle sum property in a quadrilateral. You know that this is 90 degrees. This is also 90 degrees because radius tangent 90 degrees. Radius tangent 90 degrees. Radius tangent here 90 degrees. So by using the angle sum property in a quadrilateral, 110 plus 90 plus 90 plus, you can call this X or angle PTQ, is equal to 360. That way you can find X. Now, you can give a special name, to a figure formed like this. This one will always be a cyclic quadrilateral. Which one will be a cyclic quadrilateral? Like when you take a circle, a point outside the circle, and when you draw two tangents to the circle from this external point, and and when you join the points of contact, to the center, a quadrilateral is formed, right? When you take a circle here with center O, C external point, you draw CA and CB tangents to the circle, and then you join A to O and B to O. You see a quadrilateral is formed now. This quadrilateral is a cyclic quadrilateral. Because what is a cyclic quadrilateral? A quadrilateral in which one pair of opposite sides is supplementary. Sorry, one pair of opposite angles are supplementary. So here it's always going to be 90 here and 90 here, right? It's always going to be 90 here and 90 here. And these are opposite angles. 90 plus 90, 180. In a quadrilateral, if one pair of opposite angles are supplementary, it is a cyclic quadrilateral. So that means this pair also will be supplementary because 90, 90, 180, 360 minus 180 is 180. Then this pair of angles also will be supplementary. So in that case, you don't have to do angle sum property and all that. This is 110. So this will be 180 minus 110, which is 70 straight away. Because MCQs, you don't have to show steps. You can just, work using supplementary angles. Opposite angles are supplementary in a cyclic quadrilateral. All right, so if this angle is given to be 120 degrees, 120 plus 60 is 180. That's it. 120 plus 60 is 180. So this angle is 60 degrees. This one is always a cyclic quadrilateral because 90 plus 90, 180. One pair of opposite angles are supplementary. If tangents PA and PB from a point P to a circle with center O, tangents PA and PB from P, two tangents from P, PA, PB. If tangents PA and PB from a point P to a circle with center O are inclined to each other, the tangents are inclined to each other. That means the angle between the two tangents is 80 degrees. Are inclined, the tangents are inclined to each other at an angle of 80 degrees. That means the angle between the two tangents. This is one tangent, this is the other tangent. The angle between the two tangents is 80 degrees. Inclined to each other. That means the angle between the two tangents we'll have to find this angle. Okay. So for 1 mark, you have to just give the answer, right? So these two triangles are congruent. So CPCT, you will have this angle is equal to this angle, and this angle is equal to this angle. This angle will be equal to this angle. See, these two triangles are congruent. Which two triangles? Triangle POA congruent to triangle POB. POA is congruent to POB. See, this is already 90. This is 90. This is 90. Now, this angle will be equal to this angle. And this angle will be equal to this angle. These two angles equal. These two angles equal. Because the two triangles are congruent. Okay, so 80 becomes 40 here. And now in this triangle, this is 90 and this is 40. So 90 plus 40, 130. 180 minus 130, 50 degrees. So angle POA is equal to 50 degrees. POA is 50 degrees. This triangle above and the triangle below are congruent. So CPCT, this angle will be equal to this angle. So it will be 40, 40, because the whole thing is 80, 40, 40 now. We'll have to find POA, POA, this angle, POA, this one. This is 90 degrees, this is 40 degrees. So 90 plus 40, 130, 180 minus 130, 50 degrees. Okay. This also, that figure, no, I told you. The length of a tangent from a point A. The length of a tangent from a point A at a distance 5 centimeters from the center. So the distance of this point A from the center is 5 centimeters. The length of the tangent is 4 centimeters. Find the radius of the circle. Please, you need to read this carefully. The length of a tangent, see, this is from a okay. The length of a tangent from a point A, now don't read this one, is 4 centimeters. The length of a tangent from point A is 4 centimeters. And that point A is at a distance 5 centimeters from the center of the circle. You need to read it carefully. A is the external point. Nothing is said about this, so we'll just call this P. The distance of A from the center is 5 centimeters. The length of the tangent is 4 centimeters. So how do you find the radius? Pythagoras theorem. Distance 5 centimeters from the center. Distance 5 centimeters from the center. So OA is 5. The length of the tangent is 4 centimeters. The length of the tangent is 4 centimeters. Find the radius of the circle. Two concentric circles are of radii 5 centimeters and 3 centimeters. Find the length of the chord of the larger circle, which touches the smaller circle. Two concentric circles. Okay. So this is the chord to the outer circle, and it touches the inner circle at this point P. AB is a chord to the outer circle. It touches the inner circle at P. Now, what are the radii given? This is the center. When you join O to A, that represents the radius of the outer circle, 5. When you join O to P, it represents the radius of the inner circle, which is 3. When you join OA, A is a point on the outer circle. OA is the radius of the outer circle. P is a point on the inner circle. So when you join O to P, that represents the radius of the inner circle, 5 and 3. And we know this is 90 degrees because AB is a tangent to the smaller circle at P. So radius perpendicular to tangent. So this one is a right triangle. So by Pythagoras theorem, you get AP is 4. So what will be the length of the chord? The length of the chord AB will be 4 into 2, 8 centimeters. Because again, you can use a theorem. The perpendicular from the center to the chord bisects the chord. The perpendicular from the center to the chord bisects the chord. So 1/2 of the chord is 4. So the other half also will be 4. So the length of the chord is 8. 4 plus 4, 8. A quadrilateral ABCD is drawn to circumscribe a circle. So see the figure? The quadrilateral circumscribes. So the quadrilateral is outside. A quadrilateral ABCD is drawn to circumscribe a circle. So circle inside, quadrilateral outside. Quadrilateral circumscribes. It's outside the circle. You need to prove that AB plus CD is equal to AD plus BC. So in words, now see, we can understand many things from this figure. The sides of the quadrilateral are tangential to the circle. The sides of the quadrilateral are tangential to the circle. Meaning, you can see that the sides act as tangents to the circle. See here, AB is a side of the quadrilateral, but it's a tangent to the circle at P. BC is a side of the quadrilateral, and it is a tangent to the circle at Q. CD is a tangent to the quadrilateral. Sorry, CD is a tangent to the circle, and no, I was saying something. I just lost the track of it. Sorry. AB is a tangent to the circle at P. BC. Okay, I was saying AB is a side of the quadrilateral. Okay, AB is a side of the quadrilateral, and it's a tangent to the circle at P. BC is a side of the quadrilateral, and it's a tangent to the circle at Q. CD, side of the quadrilateral, tangent to the circle at R. AD, side of the quadrilateral, tangent to the circle at S. So we say that the sides of the quadrilateral are tangential to the circle. P, Q, R, and S are the points of contact. Now, this result in words is to prove that sum of the opposite sides are equal. What are AB and CD? AB and CD, opposite sides of the quadrilateral. What about AD and BC? Opposite sides of the quadrilateral. Opposite sides. Opposite sides. And what are we doing with the opposite sides? We're adding them. Sum of the opposite sides. Sum of the opposite sides. So we'll have to prove that the sum of the opposite sides are equal. So you can write you can, like recreate the question like this. If a quadrilateral circumscribes a circle, prove that the sum of the opposite sides of the quadrilateral are equal. Sum of the opposite sides. Opposite sides are what? AB and CD. Then the other pair of opposite sides, AD and BC. Sum of the opposite sides are equal. Okay. So when you take A as the external point, the vertices of the quadrilateral are all external points of the circle. See, the points P, Q, R, S lie on the circle. Now, okay, how many points do we see? We see 8 points in all. We see 8 points in all. P, Q, R, S, they are the points on the circle. Then we see A, B, C, D. They're all outside the circle. And we know that from an external point to the circle, we can draw 2 tangents. P, Q, R, S, they lie on the circle. A, B, C, D, they lie outside the circle. So from every external point, you can draw 2 tangents to the circle. So treat A as the external point. AP and AS. AP and AS are the 2 tangents drawn from the external point A to the circle. Now consider this point B, external point B. BP and BQ are the 2 tangents drawn from the external point B to the circle. Similarly, CQ and CR are 2 tangents drawn from the external point C to the circle. DR and DS are 2 tangents drawn from the external point D to the circle. And we know that by the theorem, the tangents from an external point to the circle are equal. So DR is equal to DS. CR is equal to CQ. DB is equal to, DS is equal to DR, CR is equal to CQ, BQ is equal to BP, and AP is equal to AS. Right? So just write these results and add, and you will get this result. Now see here. So that you write it, you present it correctly. We need to get AB plus CD, right? What is AB made up of? See, you need to get this result, children. You need to get this result. AB plus CD is equal to AD plus BC, right? Now, what is AB made up of? AB, it is AP plus BP, right? AP plus BP. And then what is CD made up of? CD is CR plus DR. Just write them one below the other like this. AB is AP plus BP is AB. These two together is AB. AB plus CD, right? What is AB? What is AB? AP plus BP and CD, CR plus DR. Now just write it like this. AP is equal to what? AS. BP is equal to BQ. CR is equal to CQ. DR is equal to DS. Now add these two results. We will automatically get AP plus BP is what? AB plus CR plus DR CD is equal to what is AS plus DS? AS plus DS. AS plus DS is AD. AD plus BQ plus CQ. BQ plus CQ is BC. So the theorem we have used is tangents drawn from an external point of the circle are equal. So for this, you should write the reason as tangents from external point A are equal. Tangents from external point B are equal. Tangents from external point C are equal. Tangents from external point D are equal. So I said just break down AB, write AB as AP plus BP, and write CD, the next one, CD as CR plus DR, and then put an equal to sign. Complete this. AP is equal to APAS, BP BQ, CR CQ, DR DS. Reason: tangents from the external point A, tangents from external point B are equal. Tangents from external point C, tangents from external point D. Now add these results. AP plus BP is AB plus, when you add these two, you get CD is equal to AS and DS, AD plus BQ and CQ, BC. Hence proved. Okay. Yeah. So here, again, see, the diagram may be given, may not be given. XY and X dash Y dash are two parallel tangents to a circle. Circle. Okay. Circle XY, X, Y, and X dash Y dash, X dash Y dash are two parallel tangents to a circle with center O. And another tangent AB with point of contact C and another tangent AB with point of contact C intersecting XY at A and X dash Y dash at B. Okay, so the tangent is AB. So AB is a tangent. See here. AB is a tangent, and you can see the tangent AB touches the circle at C, point of contact C. AB intersects XY at A, and AB intersects X dash Y dash at B. See here, this is the tangent. This is the tangent. It touches the circle at C, point of contact C. Where does the tangent meet XY? At A. And where does the tangent meet X dash Y dash? At B. Prove that angle AOB is 90 degrees. You need to join to find the angle. Angle AOB, this angle, AOB is 90 degrees. All right. Okay. Again, very simple proof. Now we'll mark off the points of contact of the other two tangents also. We'll just call this P as it is called there in the figure. I'll call this Q. And there is a result which says that when you, the distance between two, excuse me, children, my phone is really disturbing me. Just yeah, thank you, children. Yeah, coming back to this. So here we have two parallel tangents, right? So there's an important result here. To a circle, or we can have two parallel tangents only at the ends of a diameter. Let's understand that first. Circle. Now, this is the diameter, okay? So when you draw a tangent through this point and through this point, these two tangents will be parallel to each other. The tangents drawn at the ends of a diameter will be parallel to each other. The tangents drawn at the ends of a diameter will be parallel to each other. So to a circle, if the tangents are parallel, then they are they are drawn at the ends of a diameter. So when you connect the points of contact, PQ will pass through the center because of the diameter. See, the tangents are parallel. If the tangents are parallel, when you connect their points of contact, that will be the diameter, and hence it has to pass through the center. In a circle or to a circle, you can draw two parallel tangents only at the ends of a diameter. You can draw tangents, but if you want two parallel tangents, they are only at the ends of a diameter. So diameter, end of a diameter. If you draw a tangent through this, end of a diameter, if you draw a tangent through this, then these two tangents will be parallel to each other. These two tangents will be parallel to each other. So here we have two parallel tangents, xy and x dash y dash are two parallel tangents. What are their points of contact? P and Q. So when you join PQ, it will pass through O because PQ has to be the diameter. Okay, so this we need to understand because if the figure is not given, children, you need to draw the diagram. And in that case, when you join PQ, it should pass through O. Okay, so remember all these details. All right. Now the proof is very simple. Join O to C. All right. Now show that this triangle is congruent to this triangle. See, we need to show that this angle is 90 degrees, children. This one is 90. All right. I'll tell you how to choose the triangles. So how do you choose the triangles? Can you see? Can we see? 1 second. This is the external point A, right? This is the external point A, right? And what is OA? OA is the distance, but OA is the distance between the center and the external point. Now there are two triangles on either sides of OA, right? You need to take up those two triangles. Similarly, B, see the other points are on the circle. That's what I'm trying to say. The other points are on the circle. P is on the circle, Q is on the circle, C is on the circle. A and B are the points outside the circle. A and B are the points outside the circle. Look at the other points. No, don't talk about X and Y, X dash and Y dash. They are away. Forget them. Okay, so look at the points P and Q on the circle. C on the circle. O is the center of the circle. So A and B are the 2 points outside the circle. Okay, so OA, OB. So take up the 2 triangles on either sides of OA. So this one and this one. And take up the 2 triangles and on either sides of OB, this one and this one. Prove that this triangle is congruent to this triangle. This triangle is congruent to this triangle. A is an external point. OA is connecting the center and the external point A. On either sides of OA, we have 2 triangles. Show that those 2 triangles are congruent to each other. In the same way, B is an external point. OB connects the center and the external point. On either sides of OB, we have 2 triangles. Show that these 2 triangles are congruent to each other. You have a lot of information. You can use different congruence rules because we have a lot of information, so that you can take care. So show that they are congruent. See, to talk about all that we have in this, when you take up these 2 triangles, you can say AP is equal to AC. Why AP is equal to AC? Because tangents from A is the external point. AP is a tangent segment. AC is a tangent segment, both from A. AP, AC are both tangent segments from A, so they are equal. Then OP is equal to OC, radius. OA is the common side. So SSS rule, the triangles are congruent. But you have a lot more information. You know that this is 90 degrees. You know this is 90 degrees because radius perpendicular to tangent. So you can use the RHS rule, SAS rule. Depending on what information you are going to list, you can use different congruence criterion. So we have 90 degrees here. We have 90 here. So you can use RHS, right angle, hypotenuse, and side. So the 2 triangles are congruent. And after that, okay, these 2 triangles are congruent. So CPCT, you will have angle 1 is equal to angle 2. Similarly, from the congruency of these 2 triangles, you will get angle 3 is equal to angle 4. From the congruency of these 2 triangles, CPCT, angle 1 is equal to angle 2. From the congruency of these 2 triangles, you will get angle 3 is equal to angle 4. Okay. Angle 1 is equal to angle 2. Angle 3 is equal to angle 4. But we know that angle 1 plus angle 2 plus angle 3 plus angle 4 is equal to 180 degrees. It's a straight line, no? Diameter. POQ is the diameter. It's a straight line. Now you need to show that 2 plus 3 is 90 because angle AOB is 2 plus 3. Angle AOB is 2 plus 3. You need to show that 2 plus 3 is 90. So instead of angle 1, you write angle 2 because 1 and 2 are equal. Plus write 2 as it is, write 3 as it is. But instead of 4, you write 3 because 3 and 4 are equal, is equal to 180 because you want only 2 and 3. So twice of angle 2 plus twice of angle 3 is equal to 180. 2 common, angle 2 plus angle 3 is equal to 180. So angle 2 plus angle 3, which is angle AOB. Angle AOB is equal to 180 by 2, 90 degrees. All right. Okay. Prove that the angle between the two tangents drawn from an external point to a circle, angle between two tangents drawn from an external point of the circle is supplementary to the angle subtended by the line segments joining the line segments, not line segment, line segments joining the points of contact to the center. Sorry. Joining the points of contact to the center. Okay. So here, circle. Okay. External point. External point. Tangent or tangents from the external point. Okay. This is the angle between the tangents. This is the angle between the two tangents. This is one part. Then points of contact. Okay. Center. What is this? This is the line segment joining the point of contact to the center. What is this? This is another line segment joining the point of contact to the center. So these are the line segments. These are the line segments joining the points of contact to the center. What is this? What is OA? OA is a line segment joining the point of contact A to the center O. What is OB? It is a line segment joining the point of contact B to the center O. Okay. So this is the angle. This is the angle between the line segments, joining the points of contact to the center. And what is this? This is the angle between the two tangents. This is one tangent, this is the other tangent. This is the angle between the two tangents. Now read the statement. Prove that the angle between the two tangents, this is the angle between the two tangents drawn from an external point to the circle, is supplementary. This angle is supplementary to a different angle. Which angle is that? To the angle subtended by the line segments joining the points of contact to the center. This angle only. This is the angle. This is the angle between the line segments joining the points of contact to the center. So you need to show that these two angles are supplementary. You need to show that these two angles are supplementary. That's easy because we know that this is 90, this is 90. These two are 90. So simply you can call them AOB and ACB, but I'll just take it as X and Y. You don't use X and Y. You can just name the angles AOB and ACB. I'll just use X and Y. So 90 plus X plus 90 plus Y is equal to 360. Because this is 90. This one we'll call it as X. This is 90 and this is Y. So 90 plus X plus 90 plus Y is 360. So 90, 90, 180, 180 on the other side. If it goes 360 minus 180 is 180 is equal to X plus Y. So X plus Y is 180. That means X and Y are supplementary angles. X and Y are supplementary angles. Because their sum is 180. So we proved that they are supplementary. Yeah, we'll wind up with this one. It's time. 12 and yeah, 12 and 13 we'll do tomorrow, and we'll take up few important questions outside NCERT in the next session tomorrow. I'll just wind up with this one. Prove that the parallelogram circumscribing a circle is a rhombus. No, I can't draw, so I'll just take the next slide. So you'll have to show that the parallelogram circumscribing a circle is a rhombus. This is a circle, and outside you see a parallelogram which circumscribes a circle. You need to prove that the parallelogram is a rhombus. ABCD is a rhombus. The same proof, children. Repeat this one. Repeat this proof. Repeat this one till here. Okay. Now, after this, what you have to do is, after this, we know that in a rhombus, all the sides are equal. Okay. Sorry. What is given there? Yeah. Okay. It's a parallelogram. Okay. We'll have to prove that this parallelogram is a rhombus. So now, work this one exactly. Now it's a parallelogram. So in a parallelogram, opposite sides are equal. Okay, we've got this result. AB plus CD is equal to AD plus BC. After this, continue like this. In a parallelogram, opposite sides are equal. Okay, so that means AB, CD, they're opposite sides, but they're equal. So you can write AB as, CD as AB itself. You can write AB plus AB is equal to, again, AD and BC are opposite sides and they're equal in a parallelogram. So you can write is equal to AD plus AD. So twice AB is equal to twice AD. So you get AB is equal to AD. AB is equal to AD. Now, when in one, I just need to take a new slide, not it. Just a minute. Yeah. Okay. So I said, repeat, you just have to do that proof where we prove that the sum of the opposite sides are equal. AB plus CD is equal to BC plus AD. We know how to prove this result. Okay. Now, the given quadrilateral is a parallelogram. So in a parallelogram, opposite sides are equal. Now, AB, CD, they're opposite sides. So write AB and instead of CD, you can write AB because they're equal. Opposite sides are equal. Here also, write BC. Now, AD can be written as BC because opposite sides are equal. So you have twice AB is equal to twice BC. AB is equal to BC. AB is equal to BC. But now you see in a parallelogram, already AB is equal to CD and BC is equal to AD in a parallelogram. Now we have this result AB is equal to BC. In a parallelogram, opposite sides are equal. So we already have these two results. Now we have proved that AB is equal to BC. Now just take some numbers. AB, supposing you take this 2. So AB is equal to BC, 2, 2. Now what is BC? 2. So I'll put 2 here. If BC is 2, then because these two are equal, this also will be 2. AB is 2. So AB is 2. So CD is also 2. Can you see everything? All the sides are equal now. all the sides are equal. When you proved AB is equal to BC, now we see that all the sides are equal. So in a parallelogram, when all sides are equal, it's a rhombus. In a parallelogram, when all the sides are equal, it's a rhombus. That's the definition of rhombus. It's a parallelogram in which all the sides are equal. So what you have to do? Just work the same proof. After this, just say in a parallelogram, opposite sides are equal. You can also do this. Instead of AB, you can write CD. And instead of AD, you can write BC. Anything. Then you will get twice CD is equal to twice BC. So 2 and 2 gets cancelled. CD is equal to BC. CD is equal to BC. That's also fine. That's also fine. That will also give you the same result. See, we're using the definition of a parallel rhombus. A rhombus is a parallelogram in which all the sides are equal. And if you remember in 9th standard, when already opposite sides are equal, to prove that all the sides are equal, it is enough you prove one pair of adjacent sides are equal. We already have opposite sides equal. We need to show that all the sides are equal. For that, you just have to prove one pair of adjacent sides are equal. So that's what we proved here. We proved that one pair of adjacent sides are equal. AB is equal to AD. So in parallelogram ABCD, adjacent sides AB and AD are equal. Then ABCD is a rhombus. All right, children. We'll meet tomorrow at the same time. That's it for today's session. Thank you so much. You may leave the call. Good night.
Thank you.
Thank you. Good night.
Thank you.
Thank you. Good night.